Dear classmates, welcome back to DFT Part 2. In this video, we are going to introduce JTAG instructions. There are mandatory instructions and optional instructions. In this video, we are going to introduce two important mandatory instructions. In this table, we can see that in JTAG standard, there are three mandatory instructions: external test or Xtest, bypass, sample, and preload. Mandatory instructions must be implemented in the JTAG. There are 6 optional instructions. The optional instructions can be decided by the designer. In this video, we will first introduce the external test instruction, followed by the bypass instruction. Before we can execute an instruction, we need to load the instruction code into the instruction register. So how can we do it? We can load the instruction code by applying the following TMS sequence. First, we initialize the JTAG by applying a sequence of 5 ones. By doing so, we will initialize the tap controller to the test logic reset state. Starting from the test logic reset state, we can then load the instruction by applying a sequence of 0, 1, 1. At this time, we are now in the right column of the tap controller. This column corresponds to the states related to the instruction register. Then we apply 2 zeros. At this time, we are now at the shift IR state. In this state, we are able to shift in the instruction register and load our instruction code. Please note that the number of zeros is equal to the total length of instruction registers of all chips on the board. After that, we can leave the state by applying a 1, 1, and eventually a 0, so that we are now back to the run test idle state. The instruction code can be loaded via the TDI input pin. In the JTAG standard, it is specified that the external test instruction code must be all zeros, and the bypass instruction code must be all ones. The other instruction codes can be specified by the designers. Now let's introduce the first mandatory instruction, the Xtest. The purpose of Xtest is to test the external of chip wire interconnects among chips. Let's revisit this old example. Suppose we want to test the bridging fault or the stuck-up fault between chip 1 and the chip 2. We can apply a 101 at the output boundary scan register, and then we can capture the response from the input boundary scan register of chip number 2. In this way, we can test the internal interconnects between two chips. So the purpose of Xtest is to test the external wires among chips. This slide explains how we execute the external test instruction. On our left hand side, it is the output boundary scan cell of chip number 1. On our right hand side, it's our input boundary scan cell of chip number 2. And this piece of wire is the wire under test. between chip number 1 and 2. In step 1, we first scan in the test data into chip number 1. To do so, we type the control signal shift DR to 1 and we pause a sequence of clock DR. In step number 2, we pause one single update DR clock. In this way, the test data is updated from the left flip-flop to the right flip-flop. In step number 3, we can now capture the response at the chip number 2. We control shift DR to 0 and we pause one single clock DR. In step number 4, we can now scan out the content in chip number 2. At this time, we control the signal shift DR to 1 and we pause a sequence of clock DR. In this way, we can observe the content in the boundary scan cell of chip number 2. Please note that during this process, the control signal mode is always equal to 1. This slide shows the state transition in the tap controller. Suppose that the instruction code has been already loaded, so that we are now in the run test idle state. Starting from this state, we apply the TMS sequence 1, so that we are now in the left column of the test controller, which corresponds to the data register. And then we apply the TMS sequence 0, 0. So now we are in the shift DR state. In this state, we are able to scan in our test data. Please note that the number of zeros is equal to the total length of data register of all chips on the board. The data register includes boundary scan register as well as bypass register. After we shift in all the test data, we apply the TMS sequence 1, 1. At this state, we can update the test data from the left flip-flop to the right flip-flop. And then we apply a 1, so that we are now back to the select DR scan state. But we are not finished yet. This slide shows the operation of boundary scan cell and the tap controller state transition of chip number 2. We apply the TMS sequence 0 to capture the response into the flip-flop. And then we apply a 0, so that we are now in the shift DR state again. We can apply a sequence of zeros to scan out the contents in the flip-flop of chip number 2. Again, the length of zeros is equal to the total length of data register of all chips on the board. After that, we apply a TMS sequence equal to 1, 1, and 0. At the end of the test, we will return to run test idle state. Now, let's show you an example. Suppose we want to test the interconnect between chip number 1 and the number 2. Starting from the beginning, this table shows the TMS and the TDI TDO sequence to apply the test. The first column shows the test access port name. We apply a sequence of 5 ones so that we can start at the test logic reset state. Then we applied a sequence of 0, 1, 1, 0, 0, so that we are now in the shift IR state. Please notice that the left bit is shift in first, and then we are able to load the instruction code into 2 chips. Suppose that chip number 2 has 3 bits of instruction register and chip number 1 has 4 bits of instruction register, so that the total length of instruction register on the board is 7. Remember that the instruction code of external test is specified to be all zeros by the JTAG standard. So we apply a sequence of 7 zeros of TMS. At the same time, there are 7 zeros in TDI. After we load the instruction code to 2 chips, we can now leave the state by applying a TMS sequence of 1, 1, and 0. Now we are in run test idle state. Starting from the run test idle state, we apply a TMS sequence of 1, 0, 0. Now we can shift in the test data. On this board, suppose that this is our TDI input. There are 8 bits of data register in chip number 1 and also 8 bits of data register in chip number 2. So there are totally 16 bits of data register on this board. So we apply 6 bits of zeros in TMS, and we apply our test input data 101. Again, please note that the test data is shifting from the left bit first. After we scan in all our test data, we can apply a sequence of 1, 1, and 1. And we are now in the select DR scan state. But we are not done yet. We need to capture the response from the chip number 2 input side. So we apply a 0 to capture the response and another 0 again. We are now in the shift DR state. We apply 16 bits of zeros in TMS and we observe the output in TDO. We expect to see high, low, and high in these 3 flip-flops. After we shift out the test data, we can now apply a sequence of 1, 1, 0. At the end of this test, we are now in the run test idle state. This finishes the external test among chip number 1 and chip number 2. Now, we will introduce the second mandatory instruction, the bypass instruction. The purpose of the bypass instruction is to provide a shortcut that bypasses scan data from TDI to TDO of a chip. If a chip is in the bypass instruction, the scan data will go through the 1-bit bypass register instead of all the boundary scan register. For example, in the following picture, suppose that chip number 2 and chip number 3 are our chip under test. If we go through chip number 1, which has 8 bits of boundary scan register, in this way we would need 8 by 3, which is 24 clocks, to shift in the data. However, if we just go through the bypass register, we need only 1 plus 8 plus 8, which is 17 clocks. So the bypass instruction can save us test time. Now it's time for you to do the quiz. Continued from our previous example. Suppose we want to test the interconnect between chip number 2 and the chip number 3. So both of them are in the Xtest mode. This is the same as before. But now we have one extra chip, chip number 1. We don't want to test chip number 1, so we want to put it in the bypass instruction. Please update the TMS TDI TDO sequence to implement the test. Please note that the bypass instruction code for chip number 1 is 11, which is only 2 bits. And the Xtest instruction code for chip number 2 and the chip number 3 are still the same as before. Now please pause the video and work on the problem. You can modify the 3 tables on the right to do this quiz. Okay, are you done yet? This exercise is actually not very difficult because there are 2 extra bits of instructions. So we add 2 bits to shift in the bypass instruction to chip number 1. That means in the instruction register, we now have 11 for chip number 1, 0000 for chip number 2, and 000 for chip number 3. The other bits remain the same. When we want to scan in our test data, we need to add 1 more bit for the bypass register. So we add a 0 and X here. This corresponds to the don't care in the bypass register of chip number 1. Similarly, when we scan out, we have 1 more extra bit of bypass register. Have you got it correctly? In summary, in this video, we have introduced 2 mandatory instructions. The external test instruction has all 0 instruction code, which tests the interconnect wire between chips. We need to scan in our test data, update the scan register, capture the response, and then we shift out. The bypass instruction provides a shortcut that bypasses the chip. This can save our total test time. Thank you for watching this video.